Hello. In the last video, we went over what U-substitution is, and it is a way to take integrals that is undoing the chain rule. And so if we're undoing the chain rule, we actually end up with a procedure. And in this example video, we are going to look at examples of indefinite integrals, where for an indefinite integral, we want to identify an inside function so that a constant multiple of its derivative appears in the integrand. And then we substitute the function and the derivative in the integral. We evaluate the new integral with respect to u, because we've turned this whole integral in terms of x into being in terms of u, and we write the result in terms of x using the substitution we made. Those are the steps we're going to be using on these 4 examples. So the first example we have is the integral of 1 over 11x plus 9. The first step is to identify what substitution we're making. There's not a lot of substitutions we could possibly make. There's a fraction going on, and a lot of times when there's a fraction, the denominator is a good place to start looking for our substitution. So looking at this, making u equal to 11x plus 9, if we take the derivative of everything here, we get du equals 11 dx. Because remember, the derivative of x is 1. So in that first step where we're identifying an inner function such that a constant multiple appears, well, the derivative of 11x plus 9 is just a constant. So its constant multiple appears. So we have u being 11x plus 9, du being 11 dx, or with a little bit of algebra, dividing both sides by 11, we get 1/11 du is the same as dx. This substitution is saying this 11x over 9, 11x plus 9 is going to become u. This dx is going to become 1/11 du. Meaning our new integral in terms of u is 1 over u times 1/11 du. Now reviewing the ideas of integrals, when I'm multiplying by a constant, I can pull that constant all the way out in front of my integral. Meaning this is really the integral of 1/11 1 over u du. And now we know this integral. This is one of our known antiderivatives, that the antiderivative of 1 over x is the natural log of x plus c. We have the integral of 1 over u. So this equals 1/11 natural log, the absolute value of u, plus c. It's an indefinite integral, so we need that plus c. We started in terms of x, however, so we need to finish in terms of x. All that means is this u is going to get replaced with what we defined it to be, 11x plus 9. So we get our antiderivative is 1/11 the natural log of 11x plus 9 plus c. Don't forget your absolute values. Don't forget plus c. But there we have the antiderivative of 1/11x plus 9. So we're going to take a look at another example. Next example is the integral of cotangent x dx. In the integral of cotangent x dx, there really doesn't look like there's much to substitute. However, we can rewrite cotangent. Cotangent is also cosine over sine. And now we know the derivative of sine is cosine, and that the derivative of cosine is negative sine. So with the correct substitution, we can easily put this in terms of u. Now it's which one is the right substitution? I said in the last problem, a good place to start looking for what to be your substitution is the denominator. So in this case, we have a denominator of sine x. So that is going to be our u. So then du is the derivative of sine. The derivative of sine is cosine. And that means what we have is cosine x dx. That will all turn into a du. And the sine x will turn into u. So this is equal to sine becomes u, so 1/u, and cosine x dx is du. We are looking at the integral of 1/u again. The integral of 1/u du is natural log of the absolute value of u plus c. And now put it back in terms of x by putting sine of x in place of u. So the antiderivative of cotangent is the natural log of the absolute value of sine of x plus c. Now, moving on to the next example. We want to find the antiderivative of cosine of the square root x plus 1 all over the square root x dx. In the last two examples, what we took to be u was the denominator, the square root x. However, in this case, there's a lot more going on in the numerator than there were in the previous examples. In the previous example, we had the derivative of the denominator and the numerator, or a constant multiple of the derivative in the numerator. The derivative of square root x is not square root x plus 1 or involving cosine in any way. But the derivative of square root x is 1/2 square root x by the chain rule. Which, seeing that square root x in the denominator is very reminiscent of what we already have going on in problem 3. We already have a square root x in the denominator. So the fact that the derivative of square root x has a square root of x in the denominator is a good indication that this might be part of our du. This might be part of the derivative. And I do have a square root of x somewhere else in this problem. I have it inside this cosine. So inside the cosine in parentheses, we have square root x plus 1. That is what we're going to set to be u. U equals the square root x plus 1. Then du is equal to the derivative of square root x, 1 over 2 square root x, plus the derivative of 1. The derivative of 1 is 0. So the 1 goes away. We have dx. We don't have the 2 here in our problem. So with a little bit of rewriting, we actually have that 2 du is 1 over square root x dx. So those two pieces together is 2 times du. Meaning with our u substitution, we get that this integral is now the cosine of what we replaced out to be u times square root x dx is now 2 du, 2 du. Or we can pull constants all the way out front. This is 2 times the integral of cosine of u du. Something we really easily can take the antiderivative of. The antiderivative of cosine is sine. So this is equal to 2 sine of u plus c. And we replace u back in to get 2 sine of the square root of x plus 1 plus c. There is our answer for the antiderivative of cosine square root x plus 1 over the square root of x dx. And now our last example. We have e to the 4 sine inverse x dx over the square root 1 minus x squared. This integral looks very complicated. There's a lot going on. We've got an e, we've got an inverse trig, we've got a square root. But knowing antiderivatives is really helpful in this case. And knowing derivatives is really helpful in this case. In particular, we know that the derivative of sine inverse is 1 over the square root 1 minus x squared. So if the derivative of sine inverse is 1 over the square root 1 minus x squared, that again points us in the direction of sine inverse should somehow be u, and the square root 1 minus x squared will be involved with the du. What's going to be helpful is taking as much as possible in as our u when we can. For an example, back on problem 3, instead of just taking u equaled the square root of x from cosine, we took the whole thing inside the parentheses. Same thing's going to apply here. Instead of just taking u is sine inverse, we're going to say u is the whole exponent of 4 sine inverse. That means the derivative is 4 times the derivative of sine inverse, or 4 over square root 1 minus x squared dx. With a little bit of rewrite, this means our antiderivative is 1/4 du is equal to 1 over the square root 1 minus x squared dx. So this denominator in the dx is going to turn into 1/4 du. And then we have e to the u, making our new integral e to the u times 1/4 du. The x became the du, and the exponent became u. The integral of e to the u, really simple. So the integral is 1/4 e to the u plus c, because we know the derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x. We get 1/4 e to the u plus c, and now put u back in terms of x to get 1/4 e to the 4 sine inverse of x plus c. And there is our answer. So when it comes to doing antiderivatives without bounds, we need to make sure we go back in terms of x and remember our plus c. But the process of U-substitution is working to make sure we can get to an integral we already know exactly how to work.